In the elementary grades, much foundational work is done in the area of geometry. Many students don't get into heavy geometry until middle or even high school, but the work that builds the base for all of that learning happens at a very young age through the elementary years. Geometry is a math concept that lends itself to concrete objects and to pictures and drawings, and this makes it especially adaptable for all the elementary grades. While academic language is important in every math concept, it's especially important in geometry where we have so many names of shapes and processes. To begin with, we need to make sure that students understand what the word geometry itself means. We need to break it apart. We need to teach the meaning of the roots. Geo, meaning earth. Metry, meaning measure. So what are we doing? We're measuring features in the earth. We're looking at features that exist. Sometimes that piece of geometry is lost. It can get lost in worksheets. It can get lost in textbook pages. It can get lost when we leave out actual objects that students can manipulate and turn and flip. The academic language of geometry can be expanded to other subjects very easily as well. When we teach the meaning of these root words, bi, tri, quad, penta, students can apply those to other areas. And we need to make sure that we do that intentionally, that we tell students they are going to see these words in other areas and give them opportunities to think of what those words are and present them with words that are outside of the math domain. In geometry, we also need to emphasize relationships and why those relationships work. There are many formulas in the area of geometry, and all of those formulas represent a relationship in the natural world. Students need to see that. Looking at geometry in the real world helps them see that this is something that is actually in nature. This is something that exists. This is something that we have developed a system to explain. After we provide students with many opportunities to actually play with shapes and objects and work with them, then we can begin the process of adding the math. One of the first things we want to be able to have students do is to see that shapes have different attributes. For example, if we look at this shape, we see that it has 4 sides. We see that it has 2 sets of parallel sides. We see that the sides are all the same length, that they are equal. We see that it has right angles. If we put all of those attributes together, then we can say this shape is a square because it has all those attributes. But this shape is also a rectangle. A rectangle has 2 sets of parallel sides and it has right angles, as does this shape. This shape is also a quadrilateral because it has 4 sides. Every quadrilateral has 4 sides. This shape is also a parallelogram because it has 2 sets of parallel sides. So students need to understand that as we add attributes, we get more and more specific with our shape names. So a square is a rectangle, but a rectangle is not a square because it does not have 4 equal sides. This gets students thinking critically. It lets them apply what they're learning. It lets them transfer that learning and express their learning in different ways. This is very important. Another way we can teach critical thinking in geometry is to make sure students understand why formulas work. For example, if we were to find the distance around this circle, we could use a formula. The formula is pi times the diameter, or 2 of the radii. So if we look at this circle, we could draw an approximate diameter. But what we want students to understand is not just that this is a formula that they can plug numbers into. We want them to understand the relationship. We can do this by having students draw a diameter, measure a string that goes across the diameter, cut the string, and then take that string around the outside. Ask students to fit the string around the outside of the circle and ask how many times does that string fit around the outside. So they take this, they curve it, and they follow the outside. And what they're going to find, of course, is that that string is going to fit 1, 2, 3, and maybe a little bit more, a little bit of a space there. If students have drawn circles that are different sizes, this is even more powerful because they can see that no matter what size the circle is, big, small, that each time that string is going to go around the outside of the circle a little bit more than 3 times. That's why this formula works. So after we teach this to students, we want to go back to that formula and we want them to be able to explain. Okay, the formula for finding the circumference of a circle is pi times the diameter. Why does that work? And in kid language, we want them to be able to say, because if I take string and go across the diameter of the circle and take it around the outside, it will always fit 3 and a little bit more times. And if they forget the formula, they can remember the meaning. And this is very valuable to them. When we teach students the formula for finding the area of a circle, we get into something a little bit more complex. But again, if students can see this, if they can use a picture to see what that formula really means, it can make it so much more meaningful to them. So for example, the formula for finding the area of a circle is pi times the radius squared. So let's break that apart. What does that mean? It means we have our number pi times a radius radius squared, right? So let's ask our students to look at the picture of a circle. And we have put a square outside the circle just to make it a little bit easier for this to be seen. So where is the radius of a circle? Well, there's one. We could have a radius almost anywhere in our circle as long as it goes from the center to the outside. There's a radius. So what does a radius squared look like? Well, what that means, of course, is that we are squaring the radius, or we are making a square out of the radius. So if we look at this whole area right there, that is radius squared. We almost want our students to have a duh moment there, where they look at r squared and they think, well, what that means is I'm making a square out of r. It needs to look like a square. So if we go back to our picture now and we say to them, here is 1 radius squared. If I were going to find the area of this entire square, just forgetting the circle for a minute, how many of these would I need? Well, I would have 1 here, I would have 1 here, I would have another one here and another one here. So if I look at each one of these smaller squares, each one of those is a radius squared. So by finding the area of the entire square, what I'm really doing is taking the radius squared times 4. 4 times the radius squared. That would give me the area of the entire square. But if I really want just the area of the circle, not those little extra corners that are right here, then what do I have to do? I have to cut off those corners. I have to get rid of those corners. And if I do that, I'm making my amount smaller. So I need to be taking my radius squared by something smaller than 4. And this is where the eyes start to light up. Ta-da! Oh, pi, the magic number pi, is smaller than 4. And if I take my radius squared times 3.14, or whatever number you use for pi, that will give me the area of just the circle. So pi is this magic number that just cuts off the corners for us, which is quite amazing. And it does that in every circle of every size because the relationship between the diameter and the radius and the sizes are all the same. The relationship doesn't change, so the magic number pi works in every case. We want students to be able to explain that, to draw a picture like this one, and to be able to say, this is why this formula works. The why is crucial to student understanding. When teaching area, we need to make sure that we connect area to something that's two-dimensional, because area has 2 ways of measuring. We can measure the width, we can measure the length, or the height, or the base, or whatever terms you want to use. We're measuring 2 different things. And we're measuring area in square units. So if I want to find the area of this, all I really have to do is to count my square units. How many of them do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the area of this is 9 square units. I can look at my circle and I can estimate the area. We just worked with the area of a circle, so we know how we could find it exactly. But I could look at this and I could say 1, 2, 3, 4, 5. Well, if I put these two together, that maybe would be about 6, and these two together would be about 7. So the area of this circle, if I estimate, would be about 7. And then I could go back to my formula and find the area and see what it looks like exactly. If I look at this triangle, how would I find the area of that? Well, again, what's the formula for finding the area of a triangle? It's half of the area of a rectangle. Why is that? Because it takes up half the space. There's my triangle, and there's that other relative space. So if I find the area of this square, I can take half of that to find the area of my triangle. The area of that square would be 9, and half of that would be 4 and 5/10, or 4 1/2. So I can look at my picture and I can say, does that make sense? 1, 2, 3. If I put this one with this one, that might make another one, 4, and there's a half, sure enough. So again, we need to teach why these formulas work, so students can explain them so they understand. If they look at this figure, and if they look at the empty space here and the empty space here, they can see that these match. This and this are the same. This and this are the same. That helps them see that if we put those two pieces together, we can figure out the area. 1, 2. If I put these two pieces together, I have 3. And if I put these two pieces together, I have 4. Because this little piece right here is the same size as this little piece. So I can move those around and make a difference so that I can fill up those to get an area of 4. When we teach surface area to students, the concepts are really not much different except for one very important thing. When they look at an object like this one, they see it as three-dimensional. And when we teach area as two-dimensional, they get a little confused. Why are we using a two-dimensional process to find the area of something that's three-dimensional? And so there's misconceptions there, the idea that area could be three-dimensional. So we need to start very clearly by explaining to students that what we're really doing is we're taking this box and we're unfolding it. We're taking this side down. We're taking this side down. We're making all of these sides and the top and the bottom into separate squares. And once it's flat, and we just have a flat version of this box, then we're finding the area of all of that. Now, if we don't want to cut it apart or take it apart and make it flat, then we can take each piece separately. We can find the area of this side, and then we can say, well, if we find the area of this, there are going to be 4 of them. 1 here, 1 here, 1 in the back, and 1 over here. So we can find the area of 1 and take it times 4, but then we also need the top and the bottom, so that adds 2 more. So we're taking the area of one side, or one face, times 6. But still, even when they understand how to find the surface area by doing that, it's important that they be able to explain back to you that the reason that works is because we can unfold this box. We can take it apart and create a flat net. We can create a flat piece that allows us to find the area because we measure 2 ways, length and height, or length and width. It's not different from finding the area of these. We're just finding the area of one part at a time and adding them all together. So when we find the area, or when we find the surface area, our label is going to be square units. It's going to be inches squared, or it's going to be centimeters squared, or something squared. Why is that? Because we're creating squares. We're measuring in square units. No matter which way we're looking at this, we're measuring in square units. When we move from area to volume, we're actually moving from 2 dimensions to 3 dimensions. In area, we measured 2 ways. 1, 2. In volume, we're measuring those same 2 ways. 1, 2. But we're also measuring a 3rd way because we have a 3rd dimension. The objects aren't flat. It's important that students understand that and that they can associate the word volume with a three-dimensional object. But before we even get to that point, we want them to understand that just like area means we're covering something, volume means we're filling something. So if we take a cube, what we're doing is we're filling this with cubes. And that's the reason that when we find volume, our units are called inches cubed or centimeters cubed, because what we're filling it with is a cubic shape. It has 3 dimensions. And again, we want our students to be able to just say, well, duh, it looks like a cube. We're using cubes to fill this object, and that's what volume is. Another thing we work quite a bit with in geometry is angles, and the idea of measuring angles with degrees. When we teach this to students, we want to make sure we give them the background. We should go into the history of it. Where does this idea of degrees come from? Once we do that, then we can work with the idea of degrees used to measure the space inside, the angles inside a shape. Many of us were probably taught that there are 180 degrees in every triangle. I remember being told that. I don't remember really understanding why that was. It's kind of fun to have students do an activity where they draw triangles, they create triangles, and they actually discover this on their own. So for example, if they draw triangles of all different types and all different shapes, it does not have to be an equilateral triangle like this. In fact, it's best if it's not. We can ask students then to cut off the angles and to line up just those little corner pieces on a line, just to see what happens. So if I numbered my angles 1, 2, 3 and I cut them off, my first angle I might put right here. Here's my first angle. My second angle I would butt right up against that one, and my third angle I would butt up against that one. So my 3 angles are now all together. And it's neat to watch students when they realize that no matter what kind of triangle they drew, no matter what their angles look like, once they put them all together like this, with their sides matching, it's always going to create a straight line. It's always going to fit on a straight line. And a straight line has 180 degrees, which is why all the angles in a triangle added up have 180 degrees, because they create a straight line. We can do the same thing with quadrilaterals. So we can ask our students to draw any 4-sided figure. It doesn't have to be like this one, it can be any kind. And we can say, let's do the same thing. Let's cut off our angles and let's put them on a straight line and see what happens. So if we number them and we start, if we move this angle, it might look like that. If we move this angle, it might look like that. If we move this angle, it might look like that. And then the fourth angle. Now I haven't matched this up exactly, but if we put those angles side by side and we have them touching each other, the first one, the second one, the third one, the fourth one, what students are going to discover is that those angles go all the way around the line. They create the straight line that we had with the triangle, and they keep going, and they make a full circle. Because they make a full circle, we know that the angles in any quadrilateral are going to add up to 360 degrees. This just makes sense. It also makes sense that our 180 is half of our 360 degrees, because we know that triangles take up half the space of a quadrilateral. We can use that knowledge that we just learned in a more advanced way. So for example, if we draw any figure, or we ask our students to draw any kind of a polygon that has more than 4 sides, just to make it interesting, we can say, okay, what did we learn before? We learned that every 4-sided figure has 360 degrees, and every 3-sided figure has 180 degrees. This is what we proved in our previous lesson. So if we look at this shape, and we can divide it into 4-sided and 3-sided figures, we can probably figure out how many degrees there are in the entire shape. So if I draw a line there, I now have one four-sided figure that has to have that many degrees in it. If I draw another line here, I've created a triangle that has to have 180 degrees in it. And if I look at what I have left, 1, 2, 3, 4, 5, I still have a five-sided figure. So I'm going to add one more line, and now I have a four-sided figure with 360 degrees and a triangle with 180 degrees. And if I add all of these up, I can find out how many degrees there are in my total shape. When many students learn this law of mathematics or this concept in mathematics, they're told this by a teacher saying, there is a formula. And the formula is the number of sides minus 2 times 180 degrees. Now, if we ask our students, why does that work? Well, let's see. We know that when we're dealing with a formula, we have to have things that are all the same. So we'd have to go back to our drawing. And when we figured out our angles, our degrees this way, it was perfectly fine. It's a logical way to do it. But if we want to use a formula, we would have to make sure we were finding things that were all the same. And in this figure, we have four-sided figures and three-sided figures. So we would have to make them all match. So if I draw another line here, that gets rid of my 360 because now I have two triangles that are 180 each. And if I draw another line here, I'm going to get rid of this 360 because now I have two triangles that are 180 each. Now if I count up how many sides I started with in my shape, 1, 2, 3, 4, 5, 6, 7, 8. I have 8 sides, that's the S in this formula. Take away 2 times 180 degrees. 8 take away 2 is 6. And 6 times 180 will give me 1080 degrees in my entire shape. Now, why did this formula work? I had 8 sides in my figure. How many triangles did I have? 1, 2, 3, 4, 5, 6. The reason this formula works is because of a law of nature. No matter what kind of a closed figure I draw that has multiple sides, I will always be able to make triangles inside. I will always be able to make 2 fewer triangles than there are sides. And some early mathematicians discovered this and came up with this formula to represent that real law in the world. So let's have students learn it in the real way. Let's have them do an activity like this and discover it. Discovering why a formula works is one of the most important things we can do in geometry or any kind of math to help students get the meaning of the math. For example, many of us remember learning the Pythagorean theorem. A squared plus b squared equals c squared. Or, if we're looking to find c and we know the other two sides, we might say c equals the square root of a squared plus b squared. Same thing, just expressed in a different way. So why does this formula work? We need students to see this. We need them to see the math. If they make a squared, what does that mean? It means they're making a square out of a. Okay, there's their square. What does b squared mean? It means they're making a square out of b. And there it is. So if students can find the area of both of these and add them together, that's going to give them what c squared is, or what we have when we make a square out of c. It's a mathematical rule or law. It's what happens in the world. It's what exists. It isn't something that somebody dreamed up. It's just a way of expressing something that's real in the world. And if students see this as it really is, then they will remember why it works. They will be able to see the math, and that helps them understand the meaning of the math. There are so many fun things to do with geometry. We have tessellations. We can take students out and have them look at the playground and find shapes. There are geometry activities that are wonderful for all ages from preschool through 8th grade that can be active and engaging with real objects, with real pictures, with students explaining their thinking, with them learning academic language. It's a fun mathematical subject.